overview of, see if we can get there, of what we're going to be talking about today. So I'd like to start with an overview of just the parabolic trough models and the technology. I'm sure most everyone on this call is familiar with that technology. It's been around for a while, and it's fairly well known and widely deployed, and so it's probably no mystery to most people. So we won't focus too much on the basics. I'd like to spend most of the time today really diving into detail on how to actually use the model for a particular case. And the one I've decided to look at here is a molten salt trough with dry cooling. And so that's different from a lot of the default configuration setup that's currently in SAM. And so setting up that project actually walks us through most of the different pieces and the different submodels and gives a good opportunity to play around with the different options. So some of the things
Mike, sorry to
yeah?
interrupt just a second. Before you carry on, I just wanted to mention that if you have questions, please feel free to type them in the chat window. We'll be monitoring those and can stop to answer them as appropriate. Thanks, Mike. Go ahead.
Sure. Yeah, so glad to hear questions as we go along. So specifically, some of the topics we'll talk about in this process are how you choose heat transfer fluid, which I've abbreviated HTF here throughout the presentation. And we'll be looking at switching from the typical oil configuration to a molten salt. And then from there, kind of all the different pieces that fall out of that. We have to modify the operating temperatures to better suit the heat transfer fluid. There's some detail that we need to look at in terms of how you configure the loop, how you size the loop, how many collectors you put in the loop. And that depends on the heat transfer fluid and the operating conditions. So we'll go through that as well. With the different operating temperatures, we run into different power cycle design point specifications. And we'll go through that, and especially relating to the dry cooling and switching from wet to dry cooling. That's a fairly common question that comes up, and so I wanted to briefly cover that. We'll look at optimization of certain design parameters, and finally optimize, after we've set up our case, we'll optimize the thermal energy storage capacity and the solar multiple. So this webinar is most useful if you have familiarity with parabolic trough technology, components, and configurations. Like I said, I won't spend a lot of time describing the basics. So some background there is helpful. It's helpful if you have a basic understanding of thermodynamics, heat transfer, and fluid mechanics. Obviously, it's not really heavy into that stuff, but there are some pieces that are easier to understand with that background. If you don't have that background, that's certainly not a big problem. You can follow along as we go. It's helpful if you have some experience using SAM. If you've seen it before, that helps. And if you have a particular interest in that on the technology side, if you're more interested in finance or cost modeling, this may be interesting to you, but it's not particularly catered for that direction. So. All right, so one brief slide on the technology and how we model it in SAM. There's kind of 4 or 5 different pieces to the parabolic trough technology. The main obvious piece is the solar field, and that consists of collectors and receivers. Collectors being the reflective component and the receiver being the thermal absorption component. There's a transport system, there's thermal energy storage and heat exchanger system for oil troughs. There's a auxiliary backup possibility, and then of course there's the power cycle. So all those pieces are accounted for in SAM. And also in SAM we've got 2 different trough models. The physical trough model uses first principles and semi-empirical models to calculate performance. So this allows the user to modify geometry and optical properties kind of at the base level and predict performance, kind of move into new design spaces there. The empirical model has been around for a longer period of time, and that's based on empirical correlations from the SEGS generating facilities in California, actual plant data from those. So if you're looking for an accurate model of a SEGS-like plant, that's probably the one to use. It's much less computationally expensive than the physical model, but it's really limited to the type or configuration, operating conditions that the SEGS plants are set up for. So we've got those two different models, and today we're focusing on the physical trough model. So in the physical trough, we do break it down by these sub-models in the same way that the technology is actually constructed. So you've got heat transfer fluid distribution and transport system, which includes the headers and the layout of the field, the piping. We've got a collector and receiver model, and you can see that up there. We actually model the receiver performance in fairly detailed fashion with optical properties and geometry using a resistive network to model that. We've got the power cycle models. That includes the steam generation system, the turbine and feed water heating systems, heat rejection, which is separate models for air-cooled, wet-cooled, and hybrid-cooled heat rejection. And then, like I said, there's a possibility of fossil backup to provide auxiliary heat during non-operational periods or for backup purposes. Finally, we've got a thermal storage system, and the thermal storage can be either direct thermal storage, where the heat transfer fluid in the tanks themselves is the same heat transfer fluid that is used in the field, or you can have an indirect system in which the heat transfer fluid is different. So that would be exemplified by the Solana plant in Arizona, where they're running oil through the field but use a molten salt as the storage medium. And in that case, you need an intermediate heat exchanger to transfer the heat in and out of storage. But SAM is able to model both of those cases. All right, so those of you who used SAM before, you know this. There's basically two types of inputs in SAM. We've got the performance model input pages, and that's where we'll go into some detail today, looking at how you actually configure the different components and add settings and configure the layout of the field, etc. And then there's the cost, financial, incentive type inputs, and we won't be spending much time on those today. All right, so with that brief introduction, what I want to do now is actually start going through this demo case, and this will take us most of the way through. There's a fair amount of detail here. So if you have questions as I go along, please do ask, and Paul, please interrupt. But we'll kind of walk through in detail how you set up each of the different components, and then what impact that setup process has on the other subsystems and optimizing the layout of the solar field. All right, so you may be asking yourself, what's interesting about molten salt? If it's just a matter of switching from a oil-based HTF to a salt-based HTF, why does that pose any special interest for our analysis today? Well, there's a couple different things. First of all, salts can operate at higher temperatures than oils can. The stability limit for, say, thermanols is around 400 degrees Celsius, where molten salts can typically operate up to 550, 600 Celsius, which allows you to run a more efficient power cycle. And so you have that potential carrot that you might be chasing after. Salt is typically lower cost than oil is. It's more energy-dense thermal storage because of the larger delta T between the hot and cold side of the field. So that even though the actual specific heat of molten salt is lower, than oil. That larger delta T overwhelms that difference, and you basically have to buy less salt to store the same amount of megawatt hours of thermal energy. If you use a salt in the field, you can actually do the direct storage case where you are not doing an intermediate heat exchanger, so you don't have to buy that heat exchanger. You don't have to incur the heat exchange penalties across that system, and so it's more efficient and less costly. Now, in terms of the benefits, those are really the 5 that I've identified. There are some other differences that are just interesting to look at, and so we'll also talk about those. So the heat transfer properties of molten salt are substantially different than oil. And so that introduces differences in the flow and in the pressure drop across the field, in the specific heat capacity. All those pieces are things we have to pay attention to as we're setting up the field. The salt has a higher solidification temperature than oil does. So that means now instead of letting our oil cool down to near ambient at night and not having substantial problems, or maybe say 100 degrees C, we have to keep that salt above 250 or 260 degrees C in order to prevent it from freezing. So the question becomes, is it worth it to implement additional freeze protection? How much is that going to be needed? Does that cost overwhelm the benefits of going to molten salt? And also at higher temperatures, you have higher thermal losses. So those are things that we can predict with the SAM model, and we can start to quantify to really understand what the benefits are versus these costs. One other issue is the corrosivity of salt, but SAM doesn't really focus on those material type issues, so that needs to be dealt with, but not necessarily in this model. Okay, so just to summarize the questions we'll be looking at, how much economic benefit can a molten salt-based trough provide? That's really what we're trying to understand. It's not worth it to do molten salt if it ends up being more costly to provide the heat trace and supplemental systems, so you might just stick with a lower temperature oil system. What are the system level design issues for a molten salt trough? Like I said, freeze protection, how do you lay out the field? Well, what does that look like? What kind of things can we do to optimize that? And finally, what thermal storage size is most cost effective? That's a question you can answer with the parametric analysis in SAM, and we'll cover that at the end. So there's a general process that I recommend people follow when they're modeling a CSP technology in SAM. And it kind of starts at the component level and works its way up to the system. So the actual workflow of how you might go in and set up a project to kind of minimize the time involved, the first thing I would recommend doing is basically you pick your receiver, your heat collection element. What technology is that? What are the actual properties and geometry associated with the receiver? Next, you go specify the component for the collector. What is the mirror system you're using? What are the optical properties? What does the off-design behavior look like? Setting all that up ahead of time then allows you to go look at the solar field layout and have up-to-date values for efficiency and thermal losses that you're going to need in that process. So after you do that, then you can go and specify the heat transfer fluid and the operating temperatures for the solar field. The third step, which is actually the most complex step, is determining the operation limits for the solar field. So we'll spend a little bit of time in this demonstration looking at how you calculate minimum and maximum mass flow rates, what should the velocities be in the field to maximize the energy output. And so all of those are fairly detailed analyses, but are an important part of setting up the system. Fourth, we configure the loop. So that means choosing the right number of collectors in the loop. Fifth, specify the power cycle design point. So that means we set the efficiency, we're setting the gross power output, the different cooling technology options, Then we move to thermal storage, update the costs and financials finally, and then go through a process of optimizing. So there are certain parameters in the model that really don't have much of a fundamental reason to be a particular value other than that they can be optimized up or down to give you performance improvement or cost improvement in your system. And so that's really something that should be part of any case that any new case that you set up should be some level of optimization, even if it's just looking at one parameter at a time to understand how does the design or how does the performance and cost of the system depend on those parameters that you don't necessarily have a reason to set any particular way. And then finally, for systems with thermal storage, it's always a good practice to optimize the level of thermal storage. All right, so what I want to do now is I'm going to kind of flip back and forth between Sam and the presentation here. So hopefully we're able to follow along, but I want to just walk through this process that I've just described in setting up a case for Sam. So we'll be setting up our molten salt trough. So we'll move over to Sam here, and I've got Sam open. We'll just go ahead and create a new file. So like I said, we're using the physical model here. And because I'm not too savvy on the cost and financial models, I always use the same one, an independent power producer. You may have a different preference for whatever you're doing. But we'll go ahead and create that case. So all of these are now set to the default values. And this should look familiar if you've used SAM already. So we'll go ahead and we'll model this plant in Tucson, Arizona. We'll leave that as the default. And if you do change the default climate, it's always a good idea to go back and re-optimize some of the parameters in the model to make sure that the climate isn't really driving or you're really optimizing your plant for the particular climate that you're looking at. So like I said, the first thing we want to do is look at the receivers and the collectors. So we'll go first to the receivers page. And let me get a little more room here. So I'm kind of assuming for those of you on listening in here that you've done some of this modeling before and you're not going to need too much instruction as we go on what these different inputs are. If you do have questions along those lines, the help menu is always very good, and that's the first place to look, and look on the forum for help. But hopefully, as I go through it, kind of becomes clear what I'm talking about. So what we're going to do here is we're going to go ahead and use the shot PTR70, and there are different options. There's a few different options you can choose from, but we'll just leave it as the default shot. And in the physical model, you can specify the actual geometry of that receiver. That includes the absorber tube, inner and outer diameters, the glass tube, inner and outer diameters, parameters on the roughness, and different options. And then down here, we've got different variant options for modeling the receiver. So anybody who's built a plant knows you can go and install these brand new receivers, and they might behave like this. You get a really good emissivity. You basically have nothing in that annulus between the glass and the tube, and so there's very low pressure in there. They're behaving how they're supposed to behave. And the heat loss is very low from these tubes. It's on the order of 150 watts per meter. Now, over time, you're going to get broken glass. So some of the vacuum between the glass and the absorber tube will be lost, and so you start getting air in there, and that increases the convective loss between the surfaces. So over time, a fraction of these receivers will degrade to worse and worse performance. So you can model that in SAM with these variations. And SAM does a weighted average of these 4 different cases as it runs through each hour. So this is kind of our default case. If you've got a brand new field, you might set the ideal performance to 1 here, but we'll just go ahead and leave this alone. The one thing we do need to do is, because we're going to be running at higher temperatures, we need to update the estimated average heat loss value to reflect that we're running at, instead of 290 to 390 degrees C like we do for oil, we're actually going to be running from 290 up to 550. So our average temperature is much higher. Heat loss is going to be higher. And so when we update this heat loss, that actually updates the expected efficiency that the interface here will use to calculate the size of the field. So this process is a little bit unclear for most people, but you provide the estimated heat loss just for the design point calculations. And then when SAM runs, it's actually got a detailed model that it looks at what the actual average heat loss is. And so this process, you're not telling it what it will be during performance, you're just helping it correctly size the field. So it won't really impact things other than the sizing of the field. So we'll go through here, and what I've done is outside of the model, and don't really have time to go through it in detail, but I've calculated for this molten salt case and these different variants what the heat loss or average heat loss will be, and I'll just go ahead and enter these numbers in here. So for this first case, the ideally performing tube, the average heat loss is about 310. In the other case, it was 590. And in the third case, where we've actually got broken glass, it ended up being very high. It was 4518 watts per meter. So now I've updated these values, and you can see that the average heat loss at design, based on this weighting, is now 333, where it was previously much lower. So that's all I wanted to do to update this HCE. And actually, if we go back and look at the solar field, you'll see here that the total loop conversion efficiency will include that number that you just provided, those heat loss numbers. Okay, so now let's move on to the collector. I'm actually going to leave all of this the same, but I just want to point out if you've got a particular collector you want to model, you can do that. So if you chose the Euro trough, it'll update the value here. We'll move back and just use the Solargenics one as the default. If you have your own, obviously you can put in the specific values in here as you like, or you can save it to a library, and there's more information on that in the help menu. All right, now moving on to the solar field. So what I want to do quickly is flip back to this presentation and just kind of take a step back and look at what are we actually doing when we switch the heat transfer fluid. So previously, the current setup is Thermanol VP1, and if you look at the properties for Thermanol, we're looking over here, so I've just picked two thermal properties. The viscosity is kind of hiding here, but it's fairly low. It's one of the lowest viscosities of the fluid that we've got in SAM. And you can imagine now if we change to molten salt, nitrate salt here, we're substantially increasing the viscosity in the fluid. And so that means we're going to have, all things equal, we're going to have a much higher pressure drop across the field. So that's something we need to think about as we're designing this. How do we manage that pressure drop? If you look at the density of Thermanol is down here, and the density of nitrate salt's up here. So density is the same. We're going to have different thermal behavior over time, basically. So these are some different pieces that start to contribute to how we actually want to design the field. So the point I'm trying to make, I guess, is if you switch the field and you keep all the geometry and everything the same, or you switch the HTF and all the geometry is the same in the field, your field is probably not going to be ideally designed for your new HTF. All right, so going and looking at the solar field again, there's a whole bunch of inputs here, and it's it can be overwhelming to really know how to deal with these. But you can kind of move one at a time through and really start to understand what's happening. So first thing what we want to do is switch to our solar salt. So we'll go up here and do that. And the first thing you notice is the operating temperature limits have changed. So if we look back at Thermanol, the stability limits are 12 to 400. Now we're looking at solar salt, and it's 238 to 593. So we need to make sure whatever we design has to be within that window. So we want to take our fluid and customize it for this case. So let's set the inlet temperature. Let's leave that where it is, because that's mostly driven by the steam saturation temperature in the boiler. But we need to increase the loop outlet temperature to something more realistic. So let's set that to 550. Next comes the flow rates. And so we've got these minimum and maximum allowable flow rates. And what this is an indication of is, okay, so we bought a field. We need to buy pumps for that field. How do we determine what the flow rate through the pumps need to be? What does the range need to be on those pumps? How far can we turn them down? How far can they operate over design? Can they operate over design? These are questions that we need to answer as we're designing the field. And so looking back at the notes in the presentation, the question here is, okay, how do we design the field for those pumps to really limit the pressure drop to an allowable value? Now you can imagine if you switch the heat transfer fluid and the viscosity goes way up, the pressure drop goes way up, you're going to actually have a large enough pressure drop across the field that the pressure at the cold header or the inlet of the field might be high enough to actually rupture the tubes, and that's obviously not something we want. So we need to make sure that we design for the pressure limits of the tubes that we're going to be using. So in the oil case, the maximum pressure drop across the field is on the order of about 20 bar or 2 megapascal. So going forward, we want to make sure that for the same tubes, we'll use the information we already have to try to match our design to keep it below 2 megapascal pressure drop across the field. So there's kind of two ways to do this. The first way is we can make these changes in the inputs and then manually run SAM, look at the output, what is the pressure drop across the field, is it acceptable? No. I'm going to go back and start changing the number of collectors and the different maximum and minimum flow rates. It's a very brute force method, and it's certainly a way that you can do it. But as an engineer, I kind of like to come in and say, well, can we actually predict or understand what the methods are or what the actual equations are that might drive this? So the second method is let's match the pressure drop by iteratively solving the pipe pressure loss equations that some of us might remember from our fluid mechanics or heat transfer days. So this is actually what we're going to do. Now this is a bit of a detailed process. I've got three or four slides to kind of walk through how to do this. So if you're not particularly interested in the technical details, now might be a good time to eat your lunch or whatever you're doing. But for those of you who are, it was very instructive for me to go through this process, and so I kind of wanted to share it with you. But we'll pick it back up with the simpler stuff in 4 or 5 minutes here. All right, so this is the real technical guts of how you can calculate pressure loss in a pipe. So you might remember this is the Moody chart, and what this plots is our Reynolds number, which is an indication of the momentum forces compared to the viscous forces in a particular fluid. And so if you calculate the Reynolds number, that gives you an indication of the friction factor, basically how much pressure loss are you going to induce in a system for a particular Reynolds number. So we'll be referring back to this as we go through, but the one line that I want to pay attention to is the smooth pipeline. It kind of simplifies the analysis. Basically, we're modeling the pipe as smooth, that the micro roughness in the piping in the field is smaller than the little disturbances in the fluid as it flows through it. So we'll just trace along this lower boundary, and as we calculate Reynolds number and update it as we go along, we'll kind of look at the friction factor. All right, so the first step, and what we're trying to do is calculate the maximum HTF velocity in the field. The first step in doing this is we want to establish basically a reference pressure loss. We're trying to match our thermal case that we already know something about with the new case, the molten salt case. So we'll use that thermal case to calculate basically a constant, a pressure, reference pressure that's just going to be a constant that we use to refer back to try to match in the process of setting up the molten salt loop. So first thing, we use the maximum thermal velocity, and if we look at SAM, we've got a, flipping back here, our maximum velocity was, it should be 5, I must have changed another setting in here. Oh yeah, my temperature. So if we go back to 390, we're looking at a maximum velocity of about 5 meters per second here. So we'll use that, let's change this back, 550, and solar salt. So our thermal velocity, VT, is 5 meters per second. Calculate the Reynolds number for that flow using the density, velocity, and the diameter of the tube, which is the inner absorber tube diameter, divide by the viscosity. That gives us 1.39 e to the 6. If you look back at the Moody chart then, and look at where is 1.39 e to the 6, it's right here at this dot. So our friction factor for the oil field is somewhere in here. It's about 0.011, something like that. And that's what I've pulled out here. So the next step is what we want to do is use this information to scale the number of collectors in the loop. So for our first case, we're just assuming the oil trough, our reference length, which is going to be our scaling factor in the loop. We just set that to 1 to start. Then we solve the pressure equation, which if you look at here, the pressure equation is friction factor equals 2 times diameter over rho velocity squared L delta P. Let's solve that for delta P. Apologize. And that becomes this equation. And our constant pressure that we're trying to match then going forward is 1610. Now, don't try to interpret this pressure as really having anything to do with the solar field itself. This is more or less just a constant that we're going to try to match in the salt case. All right, second step. Now we need to use an energy balance on the loop to try to calculate the mass flow rate for salt. So we've made an assumption already. We're starting out with the same type of setup as we had for oil. We've got this area of our collector times the efficiency of the collector times the number of the collectors times our DNI design point is equal to the energy absorbed in the loop. That's just a simple energy balance, what's coming in to the fluid. Then there's another side of the energy balance. You've got the heat added to the loop is also equal to the mass flow rate through the loop times the specific heat times the temperature rise across that loop. So those two terms actually have to equal each other at any time. And so we can take advantage of that equality to calculate then what the required salt mass flow rate would be through the loop that we'd already set up for oil. So we're just taking our existing loop, calculating a new mass flow rate based on the properties of salt. So if we do that, that becomes this equation here. And that salt flow rate ends up, in this case, being 6.4 kilograms per second. Now that compares with oil, which was somewhat higher, around 10 previously. One thing that this requires, though, is that initial guess of what does the loop look like. So because we're guessing something about the loop, that sort of indicates in future steps we're going to iterate and come back to these equations and update that guess with better, accurate more accurate values as we go through. And eventually we'll kind of hone in on what that number of SCAs, the number of collector units, should be in the field. So that's ultimately really the goal here. All right, so now the third step, we've got our mass flow rate in the loop. So now we want to calculate what the velocity of the salt is in the loop. So you can do that with that same, or just a conservation of mass equation here. So the velocity of salt is set by the mass flow rate, and that's actually 1.02. So where previously we had, for the oil case, we had 5 meters per second, the equivalent case for salt, because of the difference in properties, but assuming the same geometry, we've actually got a much lower velocity of 1.02 meters per second. So then we use that to calculate the Reynolds number, the friction factor, so we can go back to our friction factor chart here with our updated Reynolds number and pick off the new friction factor for salt. That's 75254, and then the friction factor is 0.0195. And now what we're going to do is go back and solve that pressure equation for our updated length. So remember, we started out with a length of 1. Now we solve back for this updated length, and that's an indication of, all things equal, what is the total length of the loop relative to the original length of the loop. So solving this equation, we get 5.75. So what this is telling us is that with our initial guess and the velocities and everything that we calculated, an equivalent loop length would be 5.75 times the number of collectors in the original loop. That means 46 SCAs in the loop where originally we had 8. So anybody with a skeptical eye will say, well, that's probably not right. We don't want 46 collectors. It doesn't quite seem to match what we're doing here. And there's some logic behind that. Basically, we're assuming a velocity and a pressure drop according to that original 8 SCA configuration. Well, as we increase the number of SCAs in the loop, that velocity will increase, but the pressure drop will increase at a much faster rate than the velocity increases. And so because we're trying to match pressure drop, we don't want to go all the way up in this scaling. We want to go only a fraction of the way up with our next guess in terms of how many SCAs will be in the loop. So, you know, using, I guess this is kind of where engineering judgment comes into place, where you say, I don't really know what my next guess should be. It should be somewhere between my original, which was 1, and my next one, which is 5.75. Well, let's be conservative. We don't want to be jumping all over the place. And let's just say, okay, let's double the number of loops. So I did that. I said my new length is twice the number of original, so that means we've got 16 now. And now the final step is to return to the calculations we just went through and update the mass flow rates and velocities and Reynolds number and everything, and start calculating the new length and the number of SCAs. So using this value 2, so here's one we just did all this. This is what we just did. Using the number 2 here, that corresponds to a mass flow rate of 12.8. So we've got twice the number of collectors in the loop. That means we need twice the flow to absorb that energy. That corresponds to this velocity, this Reynolds number, this friction factor, and we update to 1.68 times the original number of collectors. So that indicates, okay, my next guess should be somewhere in that range. We were a little too aggressive with our guess of 16. So we scale that down to 14 then, go back and use 14 SCAs, and do the same thing. And we walk through, and it turns out that updated length then is 2.11. So now we've kind of hit both sides of the problem. We can either do 14 collectors or we can do 16 collectors, and right in between that length is the actual ideal match in terms of pressure loss. But now we can't do 15 because you'd have asymmetric loop, and so you want to keep the number even, so it's either 14 or 16. Well, to minimize pressure drop, let's go ahead and take the shorter count, and we've calculated now that we should have 14 assemblies in the loop where previously we had 8. So that's really the most the deepest level of technical detail that we'll go into here. And it's kind of an interesting analysis from an engineering perspective to really understand how do the properties of the fluid impact what you end up with in terms of the optimum loop design. So this collector assembly corresponds with this particular mass flow rate, which is what we calculated here for number 2. And the minimum HTF flow rate also needs to be set. So let's go back in here. We've got this. This was 1.75, and this was 12.8. So now we've set these flow rates. And I'm not going to walk through it, but actually the minimum flow rate can be handled in kind of the same way, or the preferred method of calculating the minimum flow rate is to actually run a parametric on this value after we've set things up and find the optimum value there. So that's the real detail, and we've got through that. So we've got our minimum and maximum flow rates. We also need to then go and set. I'll just say that we need to set the number of collectors to what we had calculated, which is 14. Was there a question, Paul?
Yeah, Mike, there's a question going back to when you changed the temperature to 550 there, the outlet temperature. Someone's asking about changing that without changing the type of parabola. So how can you be sure to get that temperature given the collector you chose?
Right. So in this case, what we're doing is certainly there's a lot of work to be done. If you do start looking at these temperatures, there is probably a particular collector geometry or concentration ratio that is better for these higher temperatures. But in this case, what we're doing is we're effectively just adding collectors to the loop, where originally the loop outlet would be, that 390 or whatever. In a way, we're just kind of adding additional energy into the loop to increase the temperature further. So it doesn't necessarily matter what the collector geometry is in that case. It's more that we are able to add more energy than we lose in thermal losses at these higher temperatures, and so the more collectors you add, or conversely, the more you slow down the flow rate through the loop, those higher temperatures will be attainable. So, okay, so we set those values. Now let's look back at the next steps here. Now we need to catch some of these other values that are related to this. So we've got the minimum and maximum header velocity, and we need to make sure that when we design the header, the velocity in those headers is not excessive or cause excessive pressure drop. So kind of as an indication of the scaling that happened moving from thermal to solar salt, we'll do the same type of thing, and you could actually do the same type of calculation that we just did for these, but I'll just go ahead and fill these in. So this is 0.7, and this was 1.2. And so at any point, if the velocity in the header exceeds these bounds, the header diameter is actually resized at that local spot. We also need to make sure, because we've got our salt in there, that we have a freeze protection temperature sufficient to prevent it from freezing. So we look here, and that freeze protection temperature shows up. We'll do 260. So 260 is high enough to keep it above the minimum, but is also below the minimum of the operation temperature in the field. So this is another one of those parameters that we can actually optimize later. One other interesting part of this is how do we lay out the piping? And so as you do different field sizes and different loop configurations, the optimum number of field subsections, basically how many branches does the header do to get out to the individual collectors, that will change. So what I've done is after having set this up before, I went back and ran another optimization and looked at how does my price my electricity price vary with the number of the number of subsections in the field? And it turns out 8's the best here, so we'll just go ahead and use that one. All right. So that takes care of the solar field, and those are really the big parameters that we want to make sure that we address as we're going through this design process. So now we'll move on to the power cycle. So in this case, I wanted to look at a bit of a bigger power cycle, and we do need to adjust the cycle efficiency because we're operating at higher temperatures. Let's look back at the notes here. So we're going to do an air-cooled condenser, and for this location, probably a good idea to have a relatively high design point because it's a hot climate. So we choose 42 degrees Celsius in this case. That results in a condensing temperature of about 58 degrees C, which is fairly high for a conventional plant, but is more typical for CSP. So let's go ahead and set those. We're going to come down here, and we're going to do an air-cooled. You'll notice the input options change. We want to do 42 degrees Celsius. We'll leave these alone. And yeah. All right, so now the next exercise is we need to match what we just did with the cycle conversion efficiency. So our kind of default answer for SAM is we always say, have your external model available, your own detailed models, your own performance models. Use those when you can. We can't really do everything, or SAM can't do everything, and so we don't try to. We assume if you're going to change the cycle efficiency, you might have a reason for doing that. You might have your own model that you're trying to match, and so in those cases, always use the efficiencies that you model in your own systems as inputs to the tool. Now, in absence of that information, there's some practices that you can use to get just a rough estimate. So what I've done here is I want to scale a case that we know. So we know that our molten salt power tower case with a 550 degrees Celsius steam temperature has a cycle efficiency of 41.2, and that's at these operating conditions. So if we assume a 20 degrees salt to steam temperature drop, we can use Carnot scaling to adjust this efficiency, just based on the Carnot efficiency, to match our new temperature case. So we had a 550 before from the molten salt. That's the steam temperature, not the HTF temperature. Our steam temperature, assuming at 20 degrees C, is 5530. So we'll calculate the two Carnot efficiencies. In the case of the tower, it's 59. In the case of this molten salt trough, it's 58.77. And we just use that ratio to then scale our reference efficiency that we actually know from an engineering design. So doing that, we end up with cycle efficiency growth of 0.4051. So we'll go ahead and put that in here, 0.4051. We'll go ahead and we'll also change this while we're here. This should be 550. This actually doesn't end up being used in this case, but we'll just change it because it's handy. The other piece that we wanted was 150 megawatt electric output. So just as an arbitrary target to kind of show you how this works, what you want to do is typically the gross power will be somewhat more than the actual net power you get out after you account the salt pumps and the steam pumps and the different parasitics that occur in the field. And so what you can do is increase the gross power until you see the net power output that you want. So in this case, we want 150, so we can try maybe 165. Not quite. Let's look back at 166. Still not quite. 67. Okay, so this estimate gets us to our net. Now you note when we actually simulate, we don't really often hit the net value, but that's because the different pumps come on at different times and use different parasitics. This is just a rough estimate. Okay, that's the power cycle. We've got this, we got our aux heater. The last piece is the startup temperature. So what happens is when you start at the field is the field will circulate sort of closed loop without actually interacting too much with the power cycle, and it'll heat up. And eventually you get to a point where you're generating steam in the boiler and you start spinning your turbine and actually are generating power. So the question is, what temperature should that actually occur at? And that's really a question of optimization. We could use a low temperature, and of course you have constraints on the power cycle and what it can operate within. But given a power cycle that can operate over a range, you want to look at, okay, do we start operating at a low temperature very inefficiently, or do we just keep heating up, get to a little bit higher temperature before we actually start operation? That's a question of optimization. So I went back and I ran a parametric looking at different startup temperatures and came out with 360 as the best case. So we'll go in here, and here's our startup temperature, 360. Okay, and we'll leave the other things as they are. So moving through this, we're starting to run short on time. I want to save time for questions, so I'll just go ahead and set these things. We want to make sure when we look at thermal storage that we've got the same heat transfer fluid, and we do. So that means it's a direct system. So we don't have to worry about that. We'll leave, well, I guess we can change this to 15. And we're actually going to do 4 tanks or 2 parallel sets. So we'll change that one. We also need to make sure that the heaters in the system are set at adequate temperatures. So we'll go ahead and set those 260. And then we'll leave the rest of this stuff here. One thing to point out, though, is if you're curious about some of the properties, not all of them are here, but some of the properties for the fluid that's selected here are shown. So if you have questions about what's my density or specific heat going through this, when you're setting up the field, this is a good place to look. All right, finally, we'll leave the parasitics alone. But I do want to just update some of the costs to be more reflective of this case. So we'll set the storage to 30 and the power plant to 1200. So the storage cost is lower because we have a higher energy density. And the power plant is a little bit more expensive because we've got a higher power density. So that's all we'll do for that. And really, that does a lot of glossing over of what the actual detail that should go into the cost. But that's something that people will need to do kind of on their own. All right, so I think at this point, we've got the simulation all set up. So we can go ahead and run this. So it's going to, hopefully we've set everything up correctly. And it's going to run. And actually I've already run this, so we can flip over. So here's the exact same case I've already run. And we'll look at, there's a bunch of different things to potentially look at. You can do the graph data, looking at the monthly output. If you've used SAM before, this is fairly straightforward. But you can also really dive into detail on the hourly data. So one thing that we spent a lot of time on there was sizing the solar field, or sizing the loop. And so we want to make sure that that effort we put in was worth it. Did we get the pressure out that we're expecting to get out? So we can look at the solar field pressure drop, which is right here. Remember from the oil case, we were expecting something around 20 bar or 2 megapascal across the field. And in this case, what we've actually got is, yeah, about the same. So the effort that we put in there was worth it ultimately. We got out what we were expecting to get. There's a bunch of things that we can really look at here, temperature profiles and parasitic loads and things like that. But I think what I want to do right now is just quickly show you what it looks like when we take this case and do a thermal energy storage parametric. So I took the exact same case, I went to case, duplicate, and then set up a parametric simulation on the variables of solar multiple and hours of thermal storage. And so we ran over several different cases. We'll look at solar multiple of 1.8 up to 3.4. and 4 hours of thermal storage all the way up to 16. So we're looking at kind of a peaking load plant all the way up to potentially base load type plant. So if we run this, I've got the results copied over here so we don't have to wait for it. This is the actual output. So we've got LCOE, and these are the different cases of hours of thermal storage. So you can see for just a few hours of thermal storage, it doesn't make sense to really build a big solar field beyond maybe 2 or 2.2 times the design point. As you add more thermal storage, of course, you get more and more payoff for adding more solar field. And in this case, it looks like for LCOE, our hours of thermal storage is very high. So if you're just trying to minimize the average cost of producing electricity, build a relatively small power block compared to the solar field that you're building. Run it as a base load. You maximize the use of the power block. But this isn't always the entire equation. We also care about how much profit you can make from the plant, or rate of return, or a power purchase agreement price. So if you look at when it actually makes most sense to dispatch, if we go back to SAM and look at here, there's different incentives for producing at different times. And that shows up in this chart. So if we look at PPA, so power purchase agreement price, which includes that time of dispatch pricing, now what we see is the best case is not actually building a huge amount of storage. It's quite a bit of storage in this case because we've got a direct system. But it's not just it's kind of an open-ended slope. So here it actually turned out that our PPA price optimum was at 13 hours of storage with a solar multiple of about 2.8 or 3. So I went back and ran that case, and here's the final outcome of what we've been trying to do. The question of how much value can you get from building a molten salt system, with the caveats that we spent 0 time doing cost analysis. But just on the technical side, it looks like you can get a little over, at least a little over a cent benefit in PPA price just from changing the heat transfer fluid to molten salt. So there's quite a lot of energy that went into really setting up the case for this, but the outcome is a substantial benefit, especially in terms of LCOE for the system. So that basically covers what I wanted to talk about, and I'm sorry I didn't leave more time, but maybe, Paul, we can add a few minutes on here for some questions.
Yeah, I think we can stay over if there are questions. We do have one question that I'm not sure I understand. It says, could we obtain something of each component in an overall system? I think maybe it's a question about the hourly outputs and whether we can see what the energy level is at various points in the system.
Yeah. Yeah. So let's look at that. So if you look in detail, there's a couple of places to get that information. First, you can look at data tables and look at hourly data or these different pieces. And so, for example, if we cared about the optical efficiency, we could actually look for each hour of the year what the optical efficiency was. It's more helpful to look at it here. So each of these individual component performance pieces can show up, and we can look at things like, where would that be? Here's the efficiency. So this is over the year. It's obviously hard to see, but we can zoom in and maybe look at a few days. So this is the actual optical efficiency of the collector system on an hourly basis. Or we can look at the flow rate in the field, or we can look at various temperatures. So what I like to do is look at inlet and outlet temperatures from the loop and see what are those doing over time. So let me clear this off here. So here we can see over the course of a day, at nighttime the HTF in the loop cools down. Eventually you start up in the morning, the hot fluid temperature bumps up and you run at here's our 550 design temperature. and we're running the loop, and then at night it'll cool off eventually. So yeah, you can really dive into detail on these different pieces. We can also look at things like thermal losses. So these are the thermal losses from the receiver components. You can see it's fairly high for this system.
Okay, and it looks like maybe I misunderstood that question. It's about exergy, which I don't think we report.
No, we don't have specific calculations for that. What we do have is a first law loss diagram. I mean, using some of the data here, you can kind of go back and calculate exergy values yourself, but we don't report that level of detail here.
And then there's another question about your when you went through those detailed calculations earlier. You had set a reference length,
right?
To 1, and the question is about that reference length.
Right. So that I admit was a bit confusing. So let's look back at it. The idea is what we're trying to do here is basically scale the length of this loop up or down. And so in this case, it was handy if we set a reference length of 1, that we just simply multiply the number of SCAs then by this reference length to give us a scaling up and down. So it was mostly set to 1 as sort of a handy thing. Now, what that's related to is this pressure loss coefficient here. So if we were to say set our reference length to 600 meters or whatever your typical loop length might be, this pressure coefficient over here would actually be fairly close to what we actually see in the loop. But in the end, all of that would kind of divide out. It's all normalized by itself. And we'd be scaling up and down based on the ratio of that 600 meters to the new one we calculate. So it ends up just being a ratio anyways. So that's why I said, don't pay too much attention to this pressure loss coefficient. This coefficient is just related to the equations and implementing, for our convenience, a reference length of 1. Does that answer the question? I suppose we wouldn't know. But
yeah, we'll see if there's a follow-up. There's another question here. Yeah, it does answer the question. Thanks. Asking for a comment on the status of molten salt parabolic trough technology, the maturity in the market.
Yeah, good question. Yeah, why bother if this isn't if this is like a pie in the sky? But there is a molten salt trough facility currently in operation, I believe, in Italy. It's the Archimede plant, and I forgive me, I don't remember who built that. Do you know?
It's one of the Italian groups.
Yeah, so there is there's an Italian yeah, there's an Italian group that is built.
It looks like ENEA.
Yeah, that's right. Yeah.
There you go.
Thank you. So that's been in operation. There's an experimental linear Fresnel facility down at Sandia that's currently operating, and that's Arriva and Sandia partnering there. So there are people looking at this, but yeah, particularly the Italian facility, which has been operating and is apparently showing some promise. There are issues. There's issues with corrosion, like I said, in the ball joints, and that's something that is dealt with on the component design level, but it's not really something we can deal with in SAM.
There's one other question here. How do we estimate the losses?
Is that, maybe I can get clarification, the thermal losses in the field, is that what they're looking for?
Not sure if it's that or the parasitic losses. Maybe that we'll get a follow-up here.
Okay, well, so the answer to both of those quickly would be In the field, we don't estimate, we actually calculate the losses based on heat transfer relationships or detailed heat transfer models. And so if you're looking at the operation of the field, we model the temperature of the fluid as it passes through. We model the temperature of the fluid as it passes through the loop and then calculate based on our detailed loss model there. So I just saw a note that said the question about estimated watts per meter losses. I was hoping that one might slip through. So the way that I did that is I actually have in my possession the detailed model that we use in SAM here to calculate the heat loss, and so I just ran that detailed model myself. That doesn't help you guys very much, but one thing you can do is set up a case where at these temperatures you kind of run through and set each of these variations to 1, and so try to get the model to run with the different variations just as they are, and then look back in the detailed hourly data. If we look back here, you can see there's a receiver thermal loss per meter somewhere. Here it is. So this is the weighted average, but if I would have gone back and set all the variance to 0 but 1, then it would give me the actual value. And you can see here that this watts per meter loss in the receiver is 360, 370, and what did we set it to? We set it to 310. So that's a good indication that we're kind of close. So you can do that, just run each case individually, look at that output, and try to get an estimate that way. That's probably the easiest way to do it. Hopefully in the future we can improve the interface in a way that lets people actually run those calculations, but that's something that we'll kind of have to talk about internally.
Sam advised the material and receiver for each HTF.
Is this a question about the actual absorber material itself? If it is, then so we do have a couple different materials that you can model. So if you have if your tube material happens to be one of these four, that's good. But otherwise, we don't actually have the ability to input specific materials for the tube at this point.
Okay, maybe quickly, could you show how to select a location on the location resource page?
Sure. So that's just as simple as looking through and finding your location on the list. If your location is not on the list, we do have the ability to either create your own file if you have that data, or you can download a web file from one of the different resources. And Paul, you probably know more about that than I do.
Yeah, we actually have a page on the website, a weather data page that has a lot of information about where to get weather files for different locations around the world. And the help system in SAM has pretty detailed instructions about how to work with the various weather files. And I think we'll wrap up with, there's one question about somebody would like SAM to do hybrid electric power systems, to do a hybrid thermal electric system. We don't have immediate plans for that. If you have these kind of requests, it'd be helpful to post them on the SAM support forum so other people can see and we can get a discussion going about it. If we get enough of these kinds of requests, then we can start looking around for resources to make these kind of changes. But nothing in the immediate future for hybrid modeling in SAM. All right, and then there's one more, I guess, question here about receiver thickness. Is the thickness calculated by SAM to withstand stresses and corrosion?
Yeah, so the answer is no in that case. What we're actually doing is, in here you specify, the user actually specifies inner tube, diameter, outer tube. So you're basically telling it a thickness here of 0.002 meters, 2 millimeters. And that's really based on the specifications that are provided by the vendor. If it's like a shot tube, then they would have already designed that. They would have information on what the maximum allowable pressure for their system is. And so that would be something that you'd have to follow up with a vendor on. If you're looking to do your own calculations and calculate allowable stress, you can certainly do that and calculate the thickness and then go in here and adjust accordingly based on what you actually end up with for your pressure drop in the system.
Great. Well, thanks, Mike. That was a great presentation. We will be posting a recording, like I said, on the SAM website. Go to the learning page, and there's a section there for webinars. And we'll have a recording of the session and also copies of these sample files and any other materials. And if you have further questions, please feel free to post them on the SAM support forum, and we can continue the conversation there. So with that, we'll close today's webinar. Thank you very much for your participation.